All right, let's get started with our next talk. So it's my pleasure to introduce Håvard Bjerkevik, and the title of this talk is Stabilizing Multiparameter Module Decomposition.
Thank you, and thank you to the organizers for letting me speak here. It's great to be here at the first in-person ComPer. I'm hoping there will be more. What I'm going to talk about is a preprint that I put on the archive a few months ago, and you can check it out there if you want after the talk. It's about decomposing multiparameter modules and whether we can make this stable somehow, despite it's not seeming very stable at first glance. Now, I'm going to talk a lot about multiparameter modules. So the setting of the paper is n-parameter modules, and actually even more general than that. But for the purposes of this talk, you can just imagine 2-parameter modules. Like most of the interesting stuff happens already in that case. And if you know what they are already, then great. If not, then you can visualize something like this. So in a 2-parameter module, we have a vector space over some field K that I don't really care much about. Right. And so a 2-parameter module has a vector space at every point in the plane. And then we have linear transformations that go sort of upwards and to the right. And if you start at some point and you take some path through from one point to another, then if you compose the linear transformations, then what you get should not be dependent on which path you choose. So in a way, you can consider this to be some huge commutative diagram. So that's a 2-parameter module. And we're going to talk about decomposing these modules. And we have a very nice theorem, which says that if you have some 2-parameter or multiparameter module, then we only need that it's pointwise finite dimensional. Apart from that, you can be as crazy as it wants. And then we're always able to write this as a direct sum of indecomposable modules. And moreover, this is essentially unique. So if you write it as a direct sum or isomorphism as written there, then this multiset or formal sums of these indecomposables A prime is always the same up to switching out indecomposables by isomorphic indecomposables. So we have this unique decomposition essentially, which means that we can define the barcode of a module, which is just this multiset of indecomposable modules showing up in this direct sum. And this notion barcode is inspired by the 1-parameter case where you're going to see these actual bars or intervals showing up that we'll see in a moment. Now this holds for n-parameter modules in general. In the 1-parameter case, we have an even nicer result because there we know that these indecomposables are very simple. There are these interval modules. And an interval module is a module that's supported on an interval. So outside of the interval, it's just 0. And up to isomorphism inside the interval, we have just a copy of the field, so 1-dimensional vector space, and identity morphisms. So this means that if you're given some 1-parameter module that, well, here I've sort of drawn the dimension vector, then you can always write it as a direct sum of intervals. And this means that we have this nice 1-parameter pipeline where you start with a module, or I could even add a step to the left here. We have some data sets and you get a module out of it. And then you decompose the module, and then you can draw the persistence diagram, for example, as we've seen in previous talks. And this is convenient for algorithms, and because you're dealing with many small pieces instead of one big, ugly algebraic object. And one important thing when we have a pipeline like this is that we want stability. So if you take 2 modules that are similar, maybe they're just separated by some noise in the original data set, then we want the decompositions to be similar, because if they're not, then we can't really trust that the decomposition tells us something interesting about the data set. It might just depend on the noise. And luckily in 1-parameter persistence, we have such stability. I'm not going to define interleavings. Probably most of you know about them already, but essentially A and B are epsilon interleaved. Then you can think of them as being similar up to some small epsilon. And in that case, we have an epsilon matching between their barcodes. And this epsilon matching, so if you have two modules A and B, then in an epsilon matching, you're allowed to first throw away some small pieces that are of length less than 2 epsilon. And then you have to find a bijection between the remaining intervals, such that when you match two intervals together, then the endpoints should be at most epsilon apart. So that's the one parameters case. We have this really nice algebraic stability theorem, and when we have similar modules, then we have similar barcodes. And then you can hope that this generalizes to multiparameter, and unfortunately it doesn't, and it's not even close. This stability fails really badly, as this theorem shows. So what this theorem says is that you can take any two-parameter module that's finitely presented, and you can always find an indecomposable module that's arbitrarily close to that module. And if we're looking at these matchings, then what this means is that if you have this module A, this could decompose into a lot of big indecomposables, let's say. And then to have a good matching with this module A prime, you would like to find a good bijection between them. But we see here that this A prime could have just one element in the barcode. And then you have lots of elements that you can match only to one element, so there is no good matching. And this holds, as you see, for basically every module A. So so it seems like we're just very far away to having any form of stability of multiparameter decomposition. And well, I could stop the talk here and say that we give up. Decomposition is just widely unstable in the two-parameter case, but I don't want to give up. I want to look at some examples. So here is one example that's similar in spirit to what's constructed in this paper, and it's also similar to some examples given by Mike Lesnick and Magnus Botman in a previous paper, making a similar point. And what's going on here is that we have two modules A and B, and we can see that well, A has two indecomposables and B has two indecomposables. But if I now try to find, and also they're very similar to each other, they're epsilon interleaved for some small epsilon. But now if I look for a matching, then we can take, for example, I here, which is one of the elements of the barcodes of A. And if I try to match this to some bar or to some indecomposable in B, then, well, it's not similar to J, it's not similar to J prime. So there is just no good matching here. So this is one example where this stability of decomposition fails. But at the same time, we can see what's going on here. Like A and B, they're really just three squares that are exactly the same. It's just that we've added these tiny bridges here, gluing together some indecomposables. And this feels like sort of almost like cheating, like an uninteresting example, because it feels like we should be allowed to just remove these bridges. They're non-persistent anyway. We should just be able to ignore them and then match afterwards. So to do something like this, so we sort of shrink the modules a little bit, and now we have suddenly three squares on both sides, and now we can find a good matching. And this leads us to an idea for a multiparameter pipeline of decomposition. And in this pipeline, we start with a module, and then instead of decomposing directly, we first approximate the first module. So we do some surgery. And in this example we just saw, this surgery would mean removing these small bridges. And in this case, we could hope that even if our module, well, in the case where we have a module that's maybe indecomposable, but it's almost decomposable into smaller pieces, then we can first do some surgery and then decompose and get some nice description of the first module in terms of almost summons, if you want. And in this case, we could hope to get some of the advantages we had in the one parameter case, like we have some big ugly module and we split it apart, and then we have these smaller pieces, so the module is easier to visualize, and you can maybe sort of track single features apart from each other, and it could be useful for getting faster algorithms for the same reason as in the one parameter case, and so on. Now, if you want to look at this pipeline, then there are a bunch of questions you could ask. For example, algorithms are going to be important, and complexities, that sort of thing. That's not what I'm going to talk about today. Today I'm going to talk about the stability and whether this step from a module to this decomposition of the approximation, whether that can be stable in some sense. So that's the question of the day. And to do this, we need to find some tools for destroying these small bridges, for example, that we saw in the first example and that I've written up again here. And one tool that we could use is erosion. Now, I thought that erosion was something that, well, when I was going to define erosion in my paper, I went to the literature and looked for a reference, and I didn't find one. So it's like this notion of erosion was folklore. I'm not claiming to have come up with it. But in any case, what it is, well, we first identify the parts of the modules that are either about to die or that have just been born. And then we sort of delete these parts. And we can do that by taking submodules or quotient modules, so subquotients. And this, how much we delete, is determined by this parameter epsilon. And here I've chosen a suitable small epsilon such that these bridges are deleted. And here we get exactly what we want, namely that we were able to destroy these bridges. So now we have 3 components in each module. And now we have a good matching as before. So this erosion ID seems to work well in this example here. Unfortunately, it doesn't work well in general. And we can look at a slightly more complicated example to see why that is. So here we have a module A, which is just 2 copies of a square. And we have a module B, which is indecomposable. Now B is close to A in the inner leaving distance, but what happens here is essentially that in this upper tiny corner of B, we're gluing together the 2 indecomposables. And now we could hope that we just throw erosion at this upper corner disappears, it splits up, and we're good. But what happens is that B doesn't decompose, it just shrinks and stays indecomposable for a long time. So that means that this erosion ID doesn't work directly, at least. But we could try to refine this idea a bit, and instead of eroding directly, we could pick some selective erosion. So instead of eroding all of B, I'm just removing this upper right square here and not eroding anywhere else. And that gives me a module B prime, where I've deleted this upper right square. And this B prime, it decomposes into 2 indecomposables. And now we have a good matching between A and B. They both have 2 elements of the barcode, and they're both similar. So this selective erosion is, well, for now, it seems like a good idea, and it's a good enough idea that I want to write it down as a definition. So I'm defining the erosion, epsilon erosion neighborhood of A as a collection of modules that are isomorphic to one of the form A1 over A2, or A1 quotiented by A2, where, well, this is a bit technical, but A1 is squeezed between A and the epsilon image of A. And the idea here is that for small epsilon, this epsilon image is almost all of A, which means that A1 is also almost A. And similarly, or in the opposite direction, we have that A2 is something that's within epsilon of the 0 module. So here I'm taking almost all of A and modding out by almost 0, which means that for small epsilon, this thing here is close to being A. And exactly what we choose for A1 and A2 here sort of determines where we're eroding. And then I've got a couple of propositions here that I'm just going to skip through. The moral is that this epsilon erosion neighborhood behaves a lot like the epsilon inner leaving neighborhood. And actually in the following, I could have chosen to work with the epsilon inner leaving neighborhood instead of the erosion neighborhood. There are some reasons why I prefer the erosion neighborhood, but since I don't have a ton of time, I'm just going to skip that for now. And we could try to work with this erosion neighborhood directly. There is a problem with this definition too, which is that when we're doing this selective erosion, that is picking a module in the erosion neighborhood, then what we want is to be able to split apart modules. But what can happen in some cases is that we're actually glue together different summons. And that's not what we want to allow, because we want to, if we have a matching, we want that to respect this direct sum. We don't want to glue together anything. We just want to potentially split apart things. And that leads us to the final answer for the definition that we're looking for, which is an epsilon refinement. And this is essentially just an epsilon or selective epsilon erosion where we have to respect the direct sum. So here where we take A, we write it at this direct sum of indecomposables, and then we can selectively erode each indecomposables, but not the whole module. And that means that what can happen is that we have summons of A that we maybe shrink, maybe split apart, but we're not gluing together anything. And this leads us to our notion of a stabilized epsilon matching. And this stabilized epsilon matching between two modules A and B is a module that's an epsilon refinement of both A and B. And if we look at this in a diagram, then we can see that here we have two modules A and B, and I've drawn their barcodes as these bullets. And as we've seen in examples before, we might not have a good matching directly between them. So what we do instead is that we first refine the modules. So we're splitting apart potentially some of the elements of the barcodes, and then we match afterwards. And actually, when we're doing this, we can just skip the matching and just look for a common refinement of the two modules. So yeah, this is our notion of an epsilon, a stabilized epsilon matching. And this leads us to the main theorem of the paper and the talk, which is that if you have two epsilon interleaved modules A and B, then you can always find a common refinement. And that's exactly what we want. Now there is this 2R appearing here. So you could have hoped that we could start with two modules A and B that are epsilon interleaved, and it gives us a common epsilon refinement, but unfortunately that's not what this theorem tells us. Instead, it depends on this R here. And I'm assuming R to be finite, and in that case, this R is just the maximal pointwise dimension of A. And you might think that this is slightly funny and arbitrary, and it might just be a sort of an artifact of the proof that we've used, but it turns out that if you replace this 2R by either a constant or just even R divided by 5, then this theorem is just false. There's a counterexample, which hints at the fact that there are some subtleties in here that are not so obvious. Right, so this means that this theorem, up to some not too large constant, is impossible to improve. And in the case where we have a module that is that only decomposes into a small number of indecomposables, and it's not close to decomposing more, this theorem, I think, is essentially the final answer, and you're not going to be able to really improve on it. But there are some cases that I think are interesting where you can potentially improve this a lot. And that leads us to this conjecture. So now I've just written up exactly the theorem that we saw, except that I replaced the 2 by some constant C here. It turns out that this will have to be at least 3. And then this R here, which was the maximal pointwise dimension of A, is now the maximal pointwise dimension of any summand of A. And yeah, again, if we're in the setting where A is just some big indecomposable that's not close to decomposing, then this is essentially the same as the theorem. But in the case where A is or decomposes into a lot of pointwise small dimensional summons, this can be a lot stronger. And actually in a way, that's the case that I'm most interested in, because if we look at this pipeline earlier, then if you're not able to decompose or approximately decompose the modules, then nothing really changes when you do this pipeline. You're not able to gain anything more from it. But if you have a module that's close to decomposing into a lot of small pieces, that's when this pipeline could be interesting. And where you're able to sort of split apart A and work with the small pieces. And that's exactly when this conjecture is relevant. So for example, if all the summons of A are of some constant pointwise dimension or bounded by some constant, then this R here is just a constant, and you get a much stronger result. And there are a couple of other reasons why I think it would be great to prove this conjecture. One is that there is this corollary, which is about upset decomposable modules. So an upset here is an upset in R2. That this is an upset just means that if I have some point in this subset, then everything that comes after is also in this upset. And an upset decomposable module, you can visualize that's something like this. We have many copies or summons of upset modules. And right, so these are all pointwise one-dimensional, which means that this R becomes a constant, and then you get this stronger version of the conjecture. And this case is interesting to me for a couple of reasons. One is some previous work I've done on the complexity of computing or approximating the inner leaving distance. So I showed together with Magnus Botnan and Michael Kebbe that this is approximating the inner leaving distance up to a constant of less than 3 is NP hard. And we did this by working with exactly these upset decomposable modules. And if this conjecture is true, then it turns out that even though it's NP hard to compute or approximate the inner leaving distance for small c for these modules, it's actually polynomial time to compute it or approximate it, sorry, for up to a constant for which this conjecture is true. And if you have this switch where in the upset decomposable case, where it starts out as NP hard and then for weaker approximations it becomes polynomial, then I'm starting to wonder whether this could be the case in general too. And it opens the question of whether we could approximate the inner leaving distance for large constants in the general case, which would be surprising to me and very interesting. And then the second consequence of this conjecture has to do with the applications of relative homological algebra to multipersistence that have become very popular. We saw a talk on Monday by Isaac Wren about this exact topic, and I think I know at least 4 independent groups that have written papers on this. It's really in vogue at the moment. And just to repeat very quickly what's happening in this approach, you take some multiparameter module, and instead of dealing with the whole module, you find some sort of simplified barcode that describes some features of this module. And this simplified barcode is often over the form that's like these hooks or rectangles or somehow not exactly special cases of upset decomposable modules, but morally speaking, they're sort of special cases. And if you can solve this conjecture here, then I think that would open up to being able to prove a bunch of stability theorems for this relative homological algebra approach to multipersistence. And I know that some work has already been done to prove such stability results. I think one paper by, was it Botnan, Udo, Skokkola, and Botnan, if I remember correctly, where they use some weaker version of this conjecture to get some stability results. And this conjecture would strengthen that result, and I think also apply to other cases. Yeah, I think I'm almost out of time. Let me just mention a couple of things about future work. One obvious thing is I'm not recommending anyone to try because it seems like a hard problem, but be my guest. And I'm very happy if you succeed. I would love to see a proof of this. And the second thing has to do with computing, which I haven't really talked about, but when we're doing this approximation step to try to decompose the modules more, then one natural thing to do is to put all of the generators, let's say in a region, onto a single point and all the relations onto a single point. And I think that is a natural thing to do to try to make the module decompose more. But as far as I know, I think this paper by Tamal and Chin is the state of the art of decomposing multiparameter modules. Correct me if I'm wrong. But in this paper, in this paper, they decompose modules, but they specifically require the grades of the generators and relations to be distinct, which is exactly the case that I want to avoid when trying to decompose or approximately decompose a module as much as possible. So to generalize this work to the case where the grades are not distinct would be, I think would be potentially useful for this kind of framework. All right, that's all I had. Thank you.
Questions? So maybe you said this, but maybe I missed it. You have this epsilon erosion neighborhood, and why don't you always just take the maximal erosion within that neighborhood?
Because that doesn't always give you the most decomposed modules. For example, this this B here. So this is the erosion. It's still indecomposable, but this is a module in the erosion neighborhood. That's not the maximally eroded module, and this decomposes, and we want to decompose as much as possible.
So when you compute the epsilon refinement, when you actually show the picture that's mapped out later, is it well, you said you weren't going to talk about the algorithms, but that's what I want to ask about. How it seems to me you're looking at sort of decompositions of these geometric objects in the plane. Looking at sort of Minkowski sum type, like how are you getting can you get the epsilon refinement that you actually want?
I think that I'm not sure exactly how to formulate the problem, but I think in the right way of formulating this problem, finding the best refinement is gonna be NP hard. Probably. I don't have a proof or anything, but it's the problem is like the erosion, you just erode and it's easy. You just push the generators and pull the relations. But when you have to pick these specific selective erosions, then you have to make some choices, and there are a bunch of different choices you can make, and it's not obvious which is going to be the best. So I'm not too optimistic about efficient algorithms for that to get at least to get an optimal answer. Maybe there are like pragmatic solutions in practice. I don't know.
I was also thinking like how you choose this A1, A2.
Yeah, I think it's hard. I mean, I don't have a proof or anything, it just seems hard.
There's a question in the chat.
Hmm.
I guess there's a distance obtained by the erosion neighborhood, and what is the relationship with the interleaving distance?
Yes, well, it's in the paper. I don't remember it. Yeah, there is a yeah, so there is something called the erosion distance, which is what not what I'm talking about. That has to do with rank invariant. I defined something else, which I've honestly forgotten the definition, but it's within a constant of the interleaving distance. So you combine it above and below by the constant times the interleaving distance. Oh, by the way, I think I said I don't have a proof, but it might be that I don't remember exactly now, but when you look at these upset decomposable modules, then maybe you can actually formulate computing the interleaving distance as a problem of finding the sort of correct module in the erosion neighborhood. So maybe you can actually use that to prove NP hardness of some version of the problem.
Okay, let's thank Håvard one more time.